Okay, so this is a quick one in terms of radioactivity. We've got some questions on structure and properties of alpha radiation, but I thought it'd be useful to just summarise all of them very briefly. So we've got alpha radiation, beta radiation, gamma radiation. We use both of those symbols, and we've got neutron radiation. Neutron, not much to say apart from a neutron's emitted. So alpha, whoops, 2 protons and 2 neutrons are emitted. This is a helium nucleus, so I could write it as He242 plus. So it's a large positive particle, lots of momentum, so high velocity and high mass. We can say that it can go roughly 1 centimetre in air. It's stopped by paper, and we can say it's highly ionising, weakly penetrating. In here we can just say it's medium ionisation, medium penetration for beta. But if we just say beta's formed when a neutron inside the nucleus changes to a proton and an electron. That's then spat out, so the electrons are then emitted. It's a small negative particle, because obviously it's an electron. It can go about 1 metre in air, and it's stopped by several millimetres of metal. And then just go into gamma. This is a very high frequency electromagnetic wave. So, and just make sure you got that very in there. So no mass, it's light. It can go 100 plus meters in air, and it needs several centimeters of lead to stop it. And what can we say? This time it's low ionisation. Don't say it's no ionisation. So some of you on your unit test say it's got no ionisation. Low ionisation. Gamma can still ionise. It can be absorbed by an electron, and the electron can be lost. And it's got high penetration. So that's all the basics there in terms of make sure you know that off by heart and back to front. And if you don't, go onto YouTube and Google some of the videos. There's some really good videos on it. So it says, describe the structure and properties of alpha radiation and explain why alpha has the highest ionisation energies and the highest risk as a contaminant. So quite a lot to say here. So just to summarise what we did before then, so it's 2 protons. Obviously do not use shorthand like this on any of your tests. 2 neutrons. It's a helium nucleus, which means it's a large positive particle, so it's particulate in nature. The next part is, so we've done that, and now we can just go through the basics of it's got highly ionising, but it tells us here, so highly ionising, and the reason why, because it has high momentum to remove electrons from atoms. And the reason it's got high momentum is we've seen, well, momentum equals mass times velocity, so it's a big particle with lots of velocity. And the next thing we just got to do is just summarise why is it a highest risk as a contaminant. So we have to say that, well, a contaminant is when the source is in or on you. And the reason it's the highest risk as a contaminant is it's because it's got the highest ionisation levels, and that links everything all together. Okay, so the next part is what's background radiation? This is radiation in the environment. Again, I'm not using all of the words, but it's radiation in the environment is the key ideas. And it's around us all the time. We could also say that it's from the air, particularly radon, rocks, food. And if we wanted to, we could say it's from natural and artificial sources. So natural air and rocks, and artificial medicine, nuclear weapon testing. And then it says, how can it be calculated? So, well, it's get a Geiger counter. And that's really important. We're then going to just leave this on for 1 minute with no radioactive sources around, so we know other sources. And then if we repeat about 10 times, we'll have the average counts per minute. And if we wanted to, we could do counts per second if you wanted to then divide that by 60. But what's background radiation? Radiation in the environment from natural and artificial sources, such as the air and rocks for natural, nuclear waste for artificial. And how the hell do we measure it? Get the Geiger counter thing, that's the thing that I showed you beeping away. Turn it on, pick a specific time. So we're going to pick 1 minute and then measure the counts and then repeat that 10 times to work out an average. Going on to the next one, and that summarises this before we go on to half-life. So what's the difference between a contaminant and irradiation? So I'm just going to put a C and an I. So a contaminant is when the source, in fact, I'm going to use the word source, is in or on you. And that could be, you could inhale it, you could ingest it, you could place it on the skin. And a radiant this is where the source is away from you, it's at a distance. It says, which is the highest as an irradiant? Well, that's gamma. And the reason being because it's the highest penetration. So it's the highest penetration. But we could then say, unless, if it's less than 1 centimetre away, it would now be alpha, because alpha can make it that far. If it was less than 1 metre away, it would now be beta. And the reason why that distance is important is, well, now we're dealing with higher levels of ionisation. And that's more refined. So as a general rule, gamma's the highest risk as an irradiant because it can go further. However, if we start reducing that distance down and down and down, we then get to the point where alpha and beta will now be more hazardous. And that's that done.